if I just have the damper only, it will push and eventually the damper will fail. Right? It just slows the speed down, it dissipates the energy, but I need it to go back to its original condition. All these models that we see, right? For this case, right? The 100 is our desired value. That's where we want our original. Okay. Right. Now coming back to the miserable mathematical formula. Okay. So the next one that we are going to find out is known as the subsidence ratio. And I hope this is big enough. Subsidence ratio. The words are big enough. You can see. It's okay. Can you ask him for me, please? No. I'm asking the student, can you see my handwriting? Is it still small? Or is it my handwriting is untidy? Huh? Okay. I will write better. My bad. So it's my writing abilities. Is this better now? Are we okay? Good. Okay. So subsidence ratio is an indication on how fast the oscillation decays. Okay. How fast it dies down. So the formula for subsidence ratio is equal to the second overshoot amplitude divided by the first overshoot amplitude. And if we were to go back to our diagram shortly, if we were to go back to our diagram shortly, oh, sorry. And if we were to go back our diagram shortly, the first overshoot is pi. The second overshoot, so this is the first overshoot first. And over here, this is our second. So this is where we have our 3 pi on the second. On that note, when we write out the formula, this will be equal to x(x)(s) exponential function minus 3 zeta pi, okay, divided by square root of 1 minus zeta squared. And then we divide. So that's the second overshoot. And this is our first overshoot. First overshoot will occur at pi. So that's where remembering that diagram is so important. And then finally,
The answer for subsidence ratio is the exponential function is minus 2 zeta pi over 1 minus zeta squared. Okay, so that is our subsidence ratio. The next one is pretty interesting. Okay, it's causing us a lot of problem. Okay, so the next one that we are going to talk about is known as our settling time. So our settling time is Ts. Okay. So basically, the settling time is the time taken for the oscillation to settle down. Okay, to settle down. So if we were to look at the expression now, okay, xxs is equal to E minus zeta omega n Ts multiplied by xss. We ignore the sine or cosine because we want to see when it's actually settling down. Okay, so let's put a quick example for settling time. So we want to find out what is the settling time when the maximum amplitude right, when the maximum amplitude is 2% steady state. Okay. Now we have to specify a value. Okay, we have to specify a value. Any idea why? It can be 2%, it can be 5%, it can be 10%, is whatever you design on. So this 2%, right, is dependent on the user or designer. If you feel that 10% steady state oscillation is acceptable in your design, you put 10%. If you feel that 2% is required, you put in 2%. Are we clear? Okay, so it's based on your design. Okay, so as a designer, you will come up with what amplitude is desired. Yes. There's no standard at all. I mean, oh, sorry, in a bridge design, there might be, okay? But as a mechanical engineer, when you're designing a car, an aircraft, or whatsoever, you decide. It's more of like what is comfortable for a human being, okay? So you have to do experiment. I don't know. Okay, you have to do experiment. And there are data on this. So when that's the case, you put this as 0.02 XSS E minus zeta omega n Ts XSS. Okay. So we can get rid of the XSS. Okay. So we can introduce natural log on both sides. So this will be equal to minus zeta omega n Ts. Okay. So the natural log of 0.02 is minus 3.912. So to get your TS is equal to 3.912 divided by zeta omega. So that is your settling time. Okay. So now we are going to look into an example. Okay, we can look at an example, and this example I've shown before. So what we are going to do for this example, okay, we have a spring damper system. And the mass is 9.072. And this is 1250 Newton per meter. And our C, or our damper, is equal to 200 Newton second per meter. And we are given boundary condition when time is equal to 0, right? X is equal to positive 0.15 meter. And we will declare that X positive is going down this way. And when time is equal to 0, the X dot is equal to 0 meters per second. So the first thing we want to find, okay, so we are going to determine the rise time. We are also going to determine our peak time. Like to determine our percentage of overshoot. Next is our subsidence ratio. And finally, we are also going to determine our settling time. At 2%, okay, settling time at 2% x-axis. Okay. All right, I'm going to stop here. We're going to carry on tomorrow. Not tomorrow, Thursday. Friday, there will be a full lecture again, okay?
So, so if there are overshoot, if there are overshoot in electrical circuits, I think. I think
has
it's
to be.
overshoot in electrical circuits.
There has to be, because the second order differential function is still the same.
Okay.
So in electrical system, there's still overshoot. You can see them, but you need to measure with an oscilloscope.
What?
You have to measure with an oscilloscope. So to see the electrical signal.
Okay.
There is overshoot.
Can I have a quick question?
I got a